Chapter 2, Fluid Power Principles. We'll be talking about energy, fluid power energy transmission, fluid power system variable. Doesn't that just sound like a lot of fun? Our objectives, always want to see your mission, should you decide to accept it. Of course, with possible exception of Ron, most people in here think Tom Cruise whenever they think Mission Impossible. Ron and I are old enough to remember seeing the TV show, at least in reruns. I don't think either one of us are old enough to actually watch the show. Anyway, our objective is going to be to define the different states and forms of energy, explain how work, exerted force, foot pounds, power, and horsepower relate to fluid power, define Pascal's law, describe its importance in fluid power systems. Pascal's law is very much like Ohm's law in electricity. It's really simple, but it's very powerful. Not as powerful as E equals MC squared though, because then you can like vaporize people and stuff in mass quantities. Calculate force, area, and pressure. Hint, that's Pascal's law. Distinguish and describe the difference between pounds per square inch gauge, pounds per square inch absolute, bars, and kilopascals. Anybody have any clue what the difference is between gauge and absolute?
Atmospheric pressure.
What's that mean?
At sea level is the pounds per square inch absolute has 14.7 pounds added to it, to the gauge.
Whatever gauge pressure is plus atmosphere. And like Will said, at sea level is 14 plus 14.7 pounds. Average. While sea level is the same all over the world, technically it's not, because you have the moon and the sun pulling on it, creating tides. And you have high pressure, low pressure areas, and the atmosphere and all kinds of stuff. So average 14.7. And then last but not least, we're going to identify the different types of pressure gauges used in fluid power. So total energy. Fluid power system total energy is the sum of static energy, kinetic energy, and thermal energy. What is static energy?
Energy that's stored.
That'd be potential energy as well.
Energy that is stored.
Stored, not in motion. Essentially the same thing as potential energy. You know, you're right about that. Kinetic.
That's moving.
In motion. And thermal.
By heat.
Temperature, yeah. No, there is a difference between temperature and heat, by the way. It's a physics thing. They have different definitions. Hydraulic system energy transmission. Rotating mechanical energy is transferred to a hydraulic pump, which supplies hydraulic energy to the system in the form of kinetic energy or fluid flow. Rotating mechanical energy. How you reckon you get that? Matthew?
I believe it's when the connection energy is in rotational movement.
How do you get the rotational movement?
Tied to a motor.
Motor. Yep. That, by the way, is what is known as the prime mover in fluid power. Mechanical energy. Electrical energy is changed into rotating mechanical energy by the electric motor and is transmitted to the conveyor belt by a drive or by a belt drive system. So See the motor there driving the belt that's driving the pulley, the connected to the drum on the conveyor, and it's pulling the conveyor. Fluid power system differences. When making comparisons between hydraulics and pneumatics, there are differences in system variables that must be taken into consideration. System variable is a fluid type. Hydraulic systems, that's just petroleum-based oil. It doesn't always have to be petroleum-based. They do have bio fluids now that are not as harmful for the environment. There's also diethylene glycol, which is derived from petroleum, but it's far enough away that it's not petroleum anymore. And then pneumatic systems is a gas, which air typically. Can be pure nitrogen and a couple other things. Fluid cost, hydraulic systems, the cost is moderate. Hydraulic oil is not cheap, especially nowadays because nothing petroleum-based is cheap. Pneumatic system conditioning cost only. Anybody know what that means? Besides me, Matthew?
But conditioning costs, that would be the cost for conditioning the pneumatic system.
Okay. I was hoping for something more specific than that.
So conditioning, does it have to do with the actual condition of the equipment?
Condition of the fluid.
Compressing the air, running an air compressor, would that fall into it?
Yep. When you compress air, you're also compressing moisture that's in it. So, one, you're going to want to have preferably an automatic drain on your storage tank for your pneumatic system to let all the water out of it. But that only gets most of it. You will want to use some kind of a dryer. Typically is done with refrigerated drying. Once it passes through the drying system, the air is rated by temperature. It's so you got negative 15-degree air. The air is not itself 15 degrees below zero. That is the dew point. The humidity is so low that you have to get the air that cold in order to get the moisture to condense out of it. Okay. So you're literally air conditioning the air. Fluid flow, hydraulic system, it's slow, requires a pump to do it, and pneumatic system is fast, uses air expansion that you had to compress before, so technically speaking, it requires a pump also. Work capacity, hydraulic systems are capable of moving extremely heavy loads. Hydraulic systems typically run at much higher pressures than pneumatic systems do. Typical shop air in a pneumatic system is 110, 112. Pardon me, 110 to 120 pounds. Typical hydraulic system is, 5,000 pounds per square inch. So, pneumatic systems light to moderate because they have much lower pressures. However, we will learn when we study Pascal's law that the force that is applied is directly proportional to the pressure times the area that it's working on. So 150 pounds per square inch in an area this big isn't much, but you got 150 pounds per square inch on a wall that size. You can see where it'd be a considerable amount of force. Compression, slightly compressed, our hydraulic systems slightly compresses with applied force. The amount that liquids compress is so small that you can just say that they're incompressible. Okay. Yeah, you put enough pressure on it, squeeze a little bit, but not very much at all. So we're going to say incompressible. And pneumatic systems, you can smash air pretty easily. So position control. The position control using hydraulics is so good that anybody that knows what they're doing, you ever see the guys that do heavy equipment, excavators and bulldozers and all that kind of stuff. Somebody that is really good with an excavator can pick up a dime off the pavement with an excavator. That's how fine the control is on it. It's also typically used in heavy duty industrial robotics. So most robotics nowadays are servo, but they do still have hydraulic ones that need to be really, really heavy duty lifting. And you can still put it on the gnat's ass. Pneumatic systems, simply because the air is compressible, makes it less precise. Mechanical device movement, hydraulic systems is consistent and smooth, and with pneumatic systems it is fast and inconsistent, simply because air is compressible, oil is not. Fluid return system, you have to recollect the hydraulic system oil in a reservoir so you can circulate it back through again. And the pneumatic system, it is just exhausted into the atmosphere. Lubricating, oil is self-lubricating. And then the pneumatic system requires external lubrication device. When you are conditioning your air, you do an FRL, filter regulated lubricator. In that order, you filter the air first, then you regulate it to whatever pressure you want, and then you lubricate it. Most pneumatic lubricators are the little drip doodad. And I would be willing to wager that if you went and looked at every pneumatic lubricator in the entire Springfield area, not one of them is adjusted correctly. Not even one. Those people think, hey, I need to be able to see it drip. If you can see it drip, it's too much. Okay. Then one drip every minute, every 30 seconds, 5 minutes, whatever that number is, and you'll be able to see it. You need like one drip every 24 hours. So who's going to sit around and wait for 24 hours to see it drip? I'm thinking a grand total of nobody. So you can bet that your pneumatic system's got too much oil in it. Cleanliness, oil by its very nature is not clean at all, and air, the stuff that you breathe, it says clean there. Is it really? When you consider all the pollution that we have in the air today, especially if you go out to LA right now where all the smoke is from the fires, that's probably not terribly clean. Heat from friction. Heat from friction is generated through different actions in the fluid power system, such as fluid flowing through a hose or piston moving against the cylinder body. would you have thought that just the oil moving through the hose that's carrying it to wherever it needs to go would generate friction? Especially if it has to go around a bend. Because oil, just like every other substance in the known universe, abides by Newton's laws of motion. If I'm going in this direction, I'm going to want to continue going in this direction until I'm acted on by an outside force. I'm happen to be walking down the hall and Ron comes along and bumps me, I'm going to change my direction. Otherwise, I'm just going to keep on going down the hall. Same thing with the fluid in a hydraulic system. As long as it's going in a straight line, it's cool, but whenever it gets to a bend, it's going to want to keep going straight, but the bend is going to force it to go in a different direction. That creates a lot of friction. Just the oil going through the pump itself generates lots of friction. Actuators, fluid power systems, complete work using actuators such as cylinders, motors, and oscillators. An oscillator is nothing more than a couple of cylinders that are opposed to each other. And when you apply air to this one, it's going to push, there's a racket pinion system in there. Apply air to this one, it's going to push that piston that way, it's going to rotate the shaft in that direction. Whatever here is going to push in the other direction, it's going to turn the opposite way. Some of those have mechanical stops in them, so they only go, 30 degrees, 45 degrees, 90 degrees. Most of them are unrestricted, though, and will go a full 180. If it went 360 degrees, it'd be a motor. Okay, calculating work. The amount of work produced is calculated by multiplying the force that must be overcome by the distance over which it acts. So, work is defined as the force multiplied by the distance. So, hydraulic cylinder lifting up 3,800 pound car, taking it up 8 feet in the air so you can stand under it and work on it. 3,800 pounds that you need to lift. Actually more than that, because you got to lift the cylinders or the piston, the racket that are sitting on, all that stuff too, but we'll assume that it's only the 3,800 pounds here. A little over 8 feet, 3,800 times 8, 30,400. Okay. You notice that the unit of measure there is foot-pound. That is a unit of work. We're going 8 feet, that's the foot portion of it. Lifting 3,800 pounds, that's the pound portion of it. So, where the unit comes from. Calculating power. Power indicates the rate at which the work is being done. So, you're going to lift that 3,800 pound car 8 feet in 6 seconds. One, that's hauling ass. It doesn't seem like it, but that's more than a foot per second. So you actually end up doing 1,266.67 foot-pounds per second to get it up there. Quote, calculating horsepower. Horsepower is defined as a mechanical unit of measure equal to the force required to move 550 pounds 1 foot in 1 second. Shouldn't that depend on the horse? If you got an old nag that is about to retire, probably gonna lift a whole lot less or take a whole lot longer to do it than, Clydesdale in his prime. So, yeah, the reason why I've come up with horsepower is because the horse was the first power that we had. Draw the wagon, ride them across the plains, whatever. But, I guess you can use oxen and all kinds of other things. But anyway, Pascal's law. Pascal's law states that the applied force placed on a fluid will transmit undiminished in all directions. So if I put I put 1,000 pounds on top of my piston, and I do not allow the fluid to escape from that cylinder, there's going to be 1,000 pounds pushing down. It's going to try and go in all directions. We're not just going to pressurize this little bit of fluid over here, we're going to pressurize all fluid that is in that vessel.
Is that saying you have 1,000 pounds of pressure at any point on the cylinder?
Yeah. That's why the multiple arrows is going in all directions.
That's that undiminished part.
Yeah.
Got it.
So you would measure, well, it depends on surface area here, because force is pressure times area. But you would measure the same pressure there as you would there, anywhere. Okay. Area. In hydraulic systems, area typically refers to the diameter of the piston face. In this particular case, the piston face is 10 inches in diameter. The area of a circle, as think back to your geometry days in high school. Hey, no, they didn't take geometry in high school, no? Still, they still make you take geometry in high school? It's not a required course anymore? Are you taking it? I do.
I do believe I take geometry class in high school, but it was a private course, not part of the standard curriculum.
Okay.
That's different.
So anyway, in geometry, you learn that the area of a circle is the diameter squared, the diameter times itself, multiplied by 0.7854. So in that particular case, since it's 10-inch diameter, 78.54 square inches. You notice down here it says that the rod reduces the area of the piston face because the fluid can't get to that part of the piston face. There's a rod in the way. So a lot of people, if you say, hey, I've got 10-inch bore cylinder, 5 feet long, and I apply 100 pounds per square inch of pressure to both sides of it at the same time, what happens? People will invariably say it don't move anywhere because you get equal pressure on both sides. But it will move slowly to extend the rod. Simply because you have whatever diameter the rod is, less surface area on that side than you do on the side that doesn't have a rod. more area equals more force equals movement. Assuming you have enough to overcome friction and that stuff, but we're going to assume zero friction in that case. The only way that it won't move is if you have a cylinder that's got a rod on both ends and they're the same diameter. Then they'll sit there and do nothing. Yes, they do make those. Pressure is determined by the area and the force present. So, in the example there, you got 500 pounds of force and 4 square inches in area. You divide 500 by 4, come up with 125. 125 pounds per square inch of pressure in that cylinder. Fluid power formulas. Fluid power, Pascal's law. Circle is a visual representation of how formulas for pressure, force, and area are interrelated in a fluid power system. Does that look familiar to anybody else?
Yeah.
I'm upside down. Try to do it again. Looks a lot like that, doesn't it?
Yep.
Ohm's law and power formula will tell you almost everything you need to know about a DC circuit. Pascal's law will tell you almost everything you need to know about any fluid power circuit. Okay. Surface area and pressure. Less pressure is required to extend the rod and to retract one due to more surface area. Like I said earlier, you got the full 2-inch bore there, and then you have a 2-inch minus whatever the diameter is. Shade over 3/8 of an inch for the rod in that case. You have to subtract that area, not just the diameter, but the area of that from the effective area. So, why does it not, and it is working on all this area too, isn't it? So why is the force reduced?
The direction of the pressure is useless for the purpose of the piston. All that force is exerted inward on the piston rod, not downward on the piston face.
There you go. Atmospheric pressure. Here's what Will was talking about earlier. Atmospheric pressure is the pressure created by the weight of the atmosphere at sea level under standard conditions. So, at sea level, you've got enough atmosphere above you for every 1 square inch of area, 14.7 pounds acting on. So, how much force is exerted over the entire surface of the earth. Assuming, even pressure all the way around. You don't take into account any of the mountains or valleys or anything like that.
14.7 everywhere per square inch.
Oh, yeah, per square inch. I mean, how many square inches are there on the surface of the earth, and
A lot.
multiply that by 14.7.
Would it be nothing because it's even everywhere?
Good thought, no.
Okay.
Well, I see where you're coming from, but no. Where do you go below sea level? That is,
If you're below sea level, then I would say that the pressure would, as you go further down, would go up for the environment you're in.
well, why?
More atmosphere on you.
Or atmosphere above you? Yep. You ever get out to Death Valley? What is that? Arizona, New Mexico?
Things go. Valley.
It's Arizona. Where Yuma is. There's Death Valley. Look it up.
I'm doing it.
This is
Anyway, out in Death Valley, you are thousands of feet below sea level. Therefore, you got that much more atmosphere on top of you. And at the desert floor versus whenever you climb out of the valley, it can be like 20 degrees warmer in the valley of the floor of the valley versus when you were at sea level. Simply because you have that much more atmosphere on top of you.
It's California, and it's also 282 feet below sea level.
Okay. Thank you. Does it say what the average pressure is in there?
No, but I can look it up if you want.
Yeah.
All right.
And we're talking about pressure in this class, so why not? By the way, you know how that's how straw works?
You decrease the pressure inside of the straw, so the atmosphere pushes down the liquid, pushing up the straw.
When you suck on a straw, you're lowering the pressure inside of it. And atmospheric pressure is pushing down on the surface of your beverage. You know, your soda or your tea, or I guess you're weird and you drink beer through a straw. Yeah, it's the pressure, atmospheric pressure pushing down on the liquid that's outside the straw that forces it up into the straw. Kind of cool. So, the rest of this graphic, the hydraulic system, you have a vent on the tank, right there. If you don't allow atmospheric pressure to come in, one, you'll draw a vacuum on the tank, which makes it really hard to move hydraulic fluid that way. But you can also, in theory, implode the tank because the pressure will be much lower on the inside than it is on the outside. Atmospheric pressure is going to crush it. You ever see them do the trick where you just stick an empty bottle in hot water, get it hot, take it out and set it on the counter and drop a boiled egg, de-shelled, on top of it, and as it cools, it sucks the egg inside the bottle? You guys ever do that in your science class in high school? Where did you people go to school at? You don't do all kinds of cool shit like that. Or maybe that knowledge has been lost or something, I don't know.
In my science class, we got a 20-gallon or 5-gallon bucket, and
to
A bottle to explode. Just pretty much.
explode or implode?
Explode expansion. Or not like actual, but just turn that jet fuel effect out the top,
Oh,
you know?
It's not by a lot of what I'm finding. I went through a couple things and then I just decided Google was the atmospheric pressure in Death Valley. And Google is telling me it's approximately 1,013 millibars. So I couldn't find anything with the units that we're using right now.
Why don't you just?
well, you can convert millibar into PSI pretty easily through a Google convert.
How would we do that by hand though, if we wanted to?
Knock stuff out. Gauge versus absolute. The difference between gauge pressure and absolute pressure is 14.7 psi or atmosphere. So whenever you're looking at 99 and 9/10% of the gauges that are out there, it will be PSIG, which is pounds per square inch gauge. They do make them where PSIA, a pound per square inch absolute, that includes the 14.7 PSI for atmosphere. Those are for very special use cases though. Brad has an open container on his desk there. The pressure outside that can, we'll say 14.7, we'll pretend we're at sea level in optimum conditions. 14.7 on the inside and on the outside. So the can's going to remain in that shape indefinitely. You have less pressure on the inside, it's going to implode. You have more pressure on the inside, it's going to explode.
14.9 psi for Death Valley.
Just a little bit over, but it's amazing what it can do to the average temperatures.
It's like they said the recorded highest temperature there was 134 degrees Fahrenheit.
Yeah. Which is more like 110-ish in the surrounding area once you get back up to sea level.
Makes sense.
When we are talking about PSI, unless we specifically say PSIA, we're going to assume that PSIG. These little more gauges are set for gauge pressure rather than absolute. Also, anything above 14.7 psi A is pressure. Anything below 14.7 psi A is vacuum. Vacuum is typically measured in inches of mercury. It can also be inches of water, millimeters of mercury, millimeters of water, torr, T-O-R-R, millitorr, a bunch of different ways to state the same thing. You can also say negative X number of PSI. With vacuum is not just vacuum, is actually considered negative pressure. Okay. It's one thing that a lot of people don't realize. Atmospheric pressure measurement, there we go. Mercury barometer indicates atmospheric pressure with a column of mercury. No. I want to zoom, please. Thank you. Okay, so an absolutely perfect vacuum, which by the way, you cannot achieve on Earth. 29.92 inches of mercury. Absolute pressure, get all the way down to zero. That says 29.92 inches is zero, absolute, all the way across the board. I said that is not possible on Earth. Doesn't matter how hard you try. You can get really close to that, but you can't ever get there. Borden tube pressure gauge. Borden tube pressure gauge indicates pressure using the movement of a Borden tube. A Borden tube is simply a curved tube that when you apply pressure to it, it changes its shape. Try to straighten out. You know, little toys that you get for New Year's or whatever, you blow in, the little thing rolls out and you let stop blowing, it rolls back up. That's what a Borden tube does. The little toy is actually a form of a Borden tube. Anyway, that tube is attached to a linkage arm and a gear, which causes the dial to move. And they are calibrated, you know, on what type of material the tube is made out of, you know, how thick the walls are, and all that stuff. You can easily figure out how much pressure is going to cause and what deflection on it. So they are calibrated such that it's even graduations all the way around. So in theory, it takes exactly twice as much pressure on the inside of your tube to go halfway as it does to go full scale. Okay. Which, by the way, these are the major graduation marks. That one is unnumbered, but it is still a major graduation. Then you have 1, 2, 3, 4 in between there and there. So, you know, obviously this is 100, 200, 300, 400, 500, so on. So it's 100 from there to there. How much is each one of those graduations? 20. You got 120, 140, 160, 180, 200, so on. Okay. Some of you guys had problems with that when we did the lab last week. Schrader or spring-loaded piston gauge. Spring-loaded piston gauge uses fluid pressure to push against push a piston against a compression spring that is attached to a pointer. So as you put pressure on it, you're putting force against the spring. Of course, the tighter you compress the spring, the more it pushes back. Or it takes higher and higher pressure to get the needle to move farther and farther. Pretty simple mechanism. Again, the spring is calibrated to the size of the piston that's in there, whatever the scale is on. Digital pressure gauge. Digital pressure gauge converts fluid pressure into an electrical signal as an easy to read digital display. Assuming is an indicating gauge. They do make them where it is an electronic signal only. There is no local display. But that would make it a transmitter, not a gauge. Okay. So if somebody tells you they have a non-indicating gauge, you can laugh at them. They don't know what we're talking about. It works basically on the same principle as you apply pressure. There's actually most of them anyway that I've seen uses a Wheatstone bridge, which those of you guys that have electronics know what I'm talking about. Those that haven't probably don't. You have 3 fixed resistors and 1 variable resistor. The 1 variable resistor is the one that the pressure is acting on. The higher the pressure goes, the more deflection you get on the resistor, the higher the resistance goes. And you can figure out based off of the difference between it and the other 3, how much pressure is being applied. Okay. All that physics-y stuff. And then there's simply a transducer in there that says X number of resistance equals 4 milliamps of current. X number of resistance equals 20 milligrams, 20 milliamps of current. And then you say that 4 milliamps is equal to 0 psi and 20 milliamps is equal to 1,000 or whatever that number is. Okay. Some of them are smart enough to be able to change scales. See 10, 100, 1,000, basically times 10 every time. Pressure versus vacuum. Common vacuum gauge readings are from negative 1.47 inches of mercury to negative 14.7 inches of mercury. Negative 0.1 bar to negative 1.01 bar. I don't understand why, but you would think that 1 bar would be 1 atmosphere. 2 bar, 2 atmosphere, 3 bar, 3 atmosphere. And for whatever reason, a bar is not exactly equal to 14.7, which throws you off. But it's just a different way of saying the same thing. It's like talking about Fahrenheit, Celsius, inches and millimeters, whatever, miles and kilometers. Different way of saying the same thing. And that is that.